Welcome to the video help with physics problems for Physics 1A.
This video is going to cover Homework Set 3, Part 3, which is everything under the heading Gravitation and Revision. So for 1121, this is questions 9 to 14, and for 1131, this is questions 13 to 19. This is problem 9 for 1121 or 13 for 1131.
In this problem, we're asked how g, the acceleration due to gravity, varies with height above the Earth. So in this problem, we're considering the Earth with mass Earth and an object with mass object up above the Earth at some height h. Okay, so to come up with a general equation for how g varies, we have F, the force experienced by an object, the gravitational force, is equal to g, the universal gravitational constant, times the mass of the Earth, times the mass of the object over r squared. And this, we say that the acceleration due to gravity, little g, is the acceleration of this object due to this force, so that's equal to m of the object times g. So the mass of the object will cancel out and little g will equal g times the mass of the Earth over r squared, where r is not this distance h, but rather it's the distance from the centre of the Earth. So r is equal to the radius of the Earth plus the height of the object above the Earth. Okay, so in part 1 it says assume a uniform Earth and calculate the value of little g at a height of 10,000 meters above the Earth. So we just need to substitute in for this. So g is equal to 6.673 times 10 to the minus 11 times the mass of the Earth, which is 5.98 times 10 to the 24, over r squared, which is the radius of the Earth plus the 10,000. So that is equal to 6.38 times 10 to the 6 plus 10,000. Solving this on the calculator, we get 9.7717 meters per second. So we've taken all our numbers here with 3 significant figures, so let's write this as 9.77 meters per second. Or as a fraction of g, we can do 9.7717 over 9.806, and we end up with, this is equal to 0.997 g0, where g0 is the value of g on the surface of the Earth. Okay, part 2, we're now asked at a height of 200 kilometers. So we replace this 10,000 with 200,000, and then solving it on the calculator, we end up with 9.22 meters per second, which is equal to 0.940 times g0. Just doing the same thing, 9.22 divided by 9.806. Part B. In this part, you're asked to calculate how high above the Earth in Earth radii must you get for little g to fall to half its value on the Earth's surface. So on the Earth's surface, we've got little g is equal to the mass of the Earth times the radius of the Earth squared. And we want it to be half this value, and we want to find out at what height that occurs. So now we substitute into this formula here. So we've got g, mass of the Earth. Now this r is equal to the radius of the Earth plus the height. And so now we need to solve this equation here. Okay, so the g's cancel out, the mass of the Earth cancels out, and we can rewrite this as radius of the Earth plus the height squared is equal to 2 times the radius of the Earth squared. So let's get rid of the squared sign. So we've got the radius of the Earth plus the height is equal to root 2 times the radius of the Earth. And so the height is equal to root 2 minus 1 times the radius of the Earth. Solving this on the calculator, root 2 minus 1, we end up with 0.414 times the radius of the Earth, which is the answer to this problem.
This is problem 10 for 1121 or 14 for 1131.
In this problem, we have a rapidly rotating neutron star. It's got a radius of 20 kilometers, so that's 20,000 meters, and it's rotating at 1 revolution per second. So omega is equal to 2 pi radians per second, because there's 2 pi radians in a revolution. And the question asks us, what must be the mass of this neutron star? Okay, let's consider an object on the surface. Now, the resultant force is the centripetal force, which is given by m omega squared r. For this object to not be thrown off the surface, we must have the gravitational force, the mg force, overcoming this centripetal force. So we have the g mass of the object, mass of the neutron star over radius squared has to equal the mass of the object omega squared r for the limiting case when the object will just manage to stay on the surface. So the MOs will cancel out, and we have the mass of the neutron star is equal to omega squared r cubed over g. So this is equal to 2 pi squared times 20,000 cubed over 6.673 times 10 to the minus 11. Solving this on the calculator, we end up with 4.7 times 10 to the 24 kilograms. Now the question goes on, what is its density? So remember, density is equal to mass over volume, which is the mass of the planet we've got here, 4.7 times 10 to the 24. The volume is a sphere, so 4/3 pi r cubed. So solving that on the calculator, we end up with 1.41 times 10 to the 11 kilograms per meter cubed. Okay, now this is a very, very high number. It's much denser than any of the material that we find on Earth. In the neutron star, the gravitational forces are so massive that the electrons have been sucked into the nuclei of the atoms, and so you've only got neutrons existing there. So this is a very, very, very high density.
This is problem 11 for 1121 or 15 for 1131.
In this problem, we're asked about a satellite orbiting around the Earth. Here's the Earth, and we have some satellite here. Part A asks, explain why the orbit must be in the equatorial plane. Okay, well, any satellite orbiting the Earth is going to orbit about the center of gravity of the Earth, so the point right in the center of the Earth. So the options are, it can orbit in a plane like this, it can orbit over the equator. Now, if it orbits in a plane such as this, you can clearly see that the latitude's going to be changing, and so there's absolutely no way that it could stay above the same point on the Earth all the time. About the equator, it can stay above a fixed point as long as the period of its orbit is 24 hours, the same as the period of rotation of the Earth's surface. Part B, we're now asked to calculate the radius of this orbit. So for this satellite to be in a stable orbit, we must have m omega squared r, the centripetal force, is equal to g m over r squared, the gravitational force. Now omega is equal to 2 pi times the frequency, or 2 pi over the period. And we said that the period of this geosynchronous orbit must be 24 hours, so that it's always above the same spot. It circles around the Earth once every day, and so this is 24 times 60 times 60, which is equal to 86,400 seconds. Okay, so what we're trying to do is solve this for r. So let's rearrange this equation. We've got r cubed is equal to gmm over little m, so those will cancel, and we've got over omega squared, so that's 2 pi squared with a t squared up the top. Okay, so now we can substitute in values. We've got 6.673 times 10 to the minus 11 times the mass of the Earth, which is 5.98 times 10 to the 24, times t squared over 4 pi squared. Solving this on the calculator gives us 7.5455 times 10 to the 22. This is radius cubed, so taking the cubed root gives us 4.23 times 10 to the 7 meters. Okay, part C, we now need to calculate the potential energy of this satellite. The potential energy is given by minus gmm on r, so substituting in times 10 to the minus 11 times 240 times the mass of the Earth, all over the 4.23 times 10 to the 7, and this gives us minus 2.26 times 10 to the 9 joules. Okay, now the kinetic energy is equal to a half mv squared, which is equal to a half times the 240. Now the velocity is just the distance divided by the time, so the distance it travels is 2 pi r, and the time it takes to do that orbit is the 24 hours, or the 86,400 seconds. So we square this. Solving this on the calculator, we end up with 1.14 times 10 to the 9 joules. And finally, we ask for the total energy, which is just the potential energy plus the kinetic energy. So just adding this and this, we end up with minus 1.12 times 10 to the 9 joules. Now for you to think about, is it a coincidence that the magnitude of this is twice the magnitude of this? And is it a coincidence that the total energy and the kinetic energy have the same magnitude?
This is problem 12 for 1121 or 16 for 1131.
In this problem, we're considering the galaxy. We're modelling the galaxy as a sphere with the Sun at the outer edge of the sphere. The Sun has mass Sun, which is equal to 2.0 times 10 to the 30 kilograms. It travels around the centre of the galaxy here at a distance 2.2 times 10 to the 20 meters. The Sun travels once around the galaxy every 2.5 times 10 to the 8 years, which is equal to 2.5 times 10 to the 8 times 365 days times 24, we'll get it into hours, times 60 into minutes, and times 60, we'll put that into seconds. Entering this into the calculator, we end up with 7.884 times 10 to the 15 seconds. Now, we're asked to calculate the number of stars in the galaxy. If we can work out the mass of the galaxy, we can use this with the mass of the Sun, because we're told we can estimate all the stars as having the same mass as the Sun to get the total number of stars. So let's try and work out the mass of the galaxy. Okay, the centripetal force and the gravitational force are perfectly balanced to keep the Sun travelling in its circular orbit around the galaxy. So we have G, mass of the Sun, times the mass of the galaxy, over r squared is equal to the mass of the Sun, omega squared r, where omega is equal to 2 pi on t. Okay, we're trying to find the mass of the galaxy. The mass of the suns will cancel each other out and we'll end up with mass of the galaxy. This is a capital R. These are the same radius, which is the radius of the galaxy. So the mass of the galaxy is equal to 2 pi over t squared r cubed on G. We need to substitute in values, so we've got 2 pi over 7.884 times 10 to the 15 squared times r cubed, which is 2.2 times 10 to the 20 cubed, all over G, which is 6.673 times 10 to the minus 11. This gives us that the mass of the galaxy is 1.0134 times 10 to the 41 kilograms. And so the number of stars, if we estimate that they all have the same mass as the Sun, it's just the mass of the galaxy divided by the mass of the Sun, 1.0134 times 10 to the 41 over 2.0 times 10 to the 30, which is equal to 5.07 times 10 to the 10. And so we should write this. This is only an approximation, so we shouldn't give many significant figures, as assuming that all the stars have the same mass as the Sun is a massive approximation. So this is 5 times 10 to the 10 stars.
This is problem 17. It's a 1131 only problem.
In this problem we have a disk. The disk has a radius r, and we have a small mass m, a distance x from the center of the disk, and the total mass of this disk has capital M as its total mass. And we're asked in part A to calculate the net gravitational force on the body, which is little m. Okay, so to do this, what we need to do is break this disk into little components and consider the effect each little component will have on m. So let's have a component here with mass dm. Now the force on m due to this increment dm, F, is equal to g m dm over r squared, and the direction of that force will be, it's an attractive force, so it's in this direction. But now there's a bit of a trick to this question, because imagine another little component here with the same mass dm, which is exactly opposite on this disk to this first dm. In this case, the force will be in this direction, and it will have the same magnitude. This will describe the magnitude of the force, where r squared is the distance between this and this, so to be in this case the square root of x squared plus r squared, all squared. And so these have exactly the same magnitude, and you'll see that we can break this into two components, a component along x and a component along r. And these components along r are in exactly opposite directions, and any little increment of m that you take will have another increment on the opposite side, where the component along this r direction will cancel out. So all we actually need to do is consider this component. So if we take this as the angle theta, then we just need to sum up the contribution to F in the x direction. We put the integral, because if we're using little dm it means very small, so integral is the sum gm dm over r squared, which in this case is x squared plus capital R squared. And then we only need to sum these components in the x direction, so this is times cos theta. Okay, so doing this integral, we're summing up all around the loop. So the initial mass is 0 when we start, then when we've summed in all the mass components, the total mass is capital M. So we've got, these are all constants, dm is the only variable, so gm m x squared plus R squared cos theta from 0 to m, and so m is 0, that one doesn't count, so we've got gmm over x squared plus R squared cos theta. Now cos theta isn't really a nice term to have there, so if we look at the triangle which has given us cos theta, we've got an R along here, we've got an X along here, this is theta in here describing the direction of the force, and so cos theta is equal to adjacent over the hypotenuse. And so substituting this in here, we have gmmx over x squared plus R squared to the 3 on 2. And that's our answer for the force. Okay, part B, we're asked to calculate the total gravitational potential. Now this is actually slightly easier because with the force, you saw that some of the components of the force cancelled just because of the different directions of the force from the different increments around the ring. Well, an energy doesn't have a direction, it's only got a sign. So we're not going to have gravitational potential energy cancelling out in the same way. So the total gravitational potential energy will just be if we sum up the contribution through to each of these increments. Don't need to consider the direction, so it's gm dm over R squared plus x squared to the 1/2. This is over R, that's the distance of m from the ring. We've got a negative sign there for our potential energy, and we're adding up all around the ring, so from mass 0 to m. Solving this integral, very simple, there's no functions of capital M in here, so this is equal to minus gmm over R squared plus x squared to the 1/2. Part C. In this part, we release the mass little m from rest, and we're asked to calculate its speed as it passes through the middle of our loop. Well, to do this, we need to consider the energy. The initial kinetic energy plus the initial potential energy will equal the final kinetic energy plus the final kinetic energy. Initially, the kinetic energy is 0 as it's released from rest, and we just came up with an expression for the initial potential energy. It was equal to minus gm m over R squared plus x squared to the 1/2. Now the final kinetic energy will be a 1/2 mv squared. We're trying to find this v. Final potential energy, this distance is x, so we'll just need to substitute x equals 0 into this equation to get the potential energy at this point. So this is minus gm m over R squared to the 1/2, so that's R. Okay, so let's rearrange. We can get rid of all these m's. And so we want to find out what v squared is. So we've got a half v squared is equal to gm on R minus gm over R squared plus x squared to the 1/2. So v squared is equal to, taking out all the common factors, 2gm. Now we've got 1 on R minus 1 over R squared plus x squared to the 1/2. And so v is equal to the square root of this. So 2gm, 1 on R minus 1 over R squared plus x squared to the 1/2 to the 1/2. There we go, that is our final answer. Okay, we're up to the revision. This is question 13 for 1121 or 18 for 1131. We're told that a particle follows the trajectory given by 3ti plus 1 plus t squared in the j direction, and that this particle has a mass equal to 2 kilograms. In part A of the question, we're asked to sketch a trajectory for this particle. So we need to find out the relationship between the x components and the y components. So the x component is given by 3t, so we can write this as t is equal to x on 3. The y component is given by 1 plus t squared, so if we substitute in for t here, we'll get a relationship between y and x. So this is 1 plus x squared on 9. Okay, so let's sketch this trajectory. Here's our x component, here's our y component. When x is 0, y is 1. And then it just increases like a parabola. So this is our trajectory here. Now part B says calculate the velocity and acceleration of the particle. The velocity is given by dr dt. So we need to take the derivative of this function with time. So in the I direction, 3t, take the derivative, we get 3i. In the j direction, we need to take the derivative of 1 plus t squared, which is just 2t in the j direction. So that's meters per second. For the acceleration, we take the derivative of the velocity or the double derivative of the position. So the derivative of 3i is 0. The derivative of 2t is 2j. And that's meters per second per second. Part C says determine the force acting on the particle. Just use Newton's second law. F is equal to ma. M we're told is 2. So this is equal to 4j newtons. Part D says calculate the vector torque and angular momentum of the particle about the origin. Okay, torque is given by r cross f. Sorry, that's not the unit vector, it's the radial vector. So to do this, to find the cross product, we can find the determinant of the matrix. R is given up here, so it's 3t in the I direction, 1 plus t squared in the j direction, no k component. F, we're told we calculated was 4j, so that's 0, 0. Finding the determinant of this matrix, it's got nothing in the I direction, it's got nothing in the j direction. In the k direction, it's 3t times 4, so that's equal to 12tk. Okay, and then we're asked to find the angular momentum as well. Now, angular momentum is equal to r cross p, the momentum, and the momentum is given by mv. Okay, so find the determinant of the matrix. R is the same, so that's 3t, 1 plus t squared, 0. mv, v is over here, so we need to multiply that by 2. So that is 6 in the I direction, 2 times 2t is 4t in the j direction, and nothing in the k direction. Finding the determinant, I component 0, j component 0. In the k component, we've got 3t times 4t, so that's 12t squared, minus 6 times 1 plus t squared. This is in the k direction. So this is 12t squared minus 6t squared, so that's 6t squared minus 6. Okay. Okay, so that's the answer to part D. To part E, it says, show that your result in D satisfies that the torque is equal to dl dt. Okay, let's calculate dl dt. We need to take the derivative of this with time. So the derivative of this is 12t. The derivative of 6 is 0, and this is in the k direction. This is equal to this, so this is equal to the torque. So we've shown that dl dt is equal to the torque in this case. Okay, the final problem in this set, problem 14 for 1121, which is problem 19 for 1131. Now we have an alpha particle. It's travelling along and it collides with a stationary oxygen nucleus. the alpha particle is scattered at an angle of 64 degrees to the direction of its original velocity. So this is the alpha particle, this is 64 degrees. This is the momentum of the alpha particle. And the oxygen nucleus recoils at an angle 51 degrees on the other side of the initial direction. Okay, so down here, 51 degrees, this is the momentum of the oxygen atom nucleus. So here's the oxygen nucleus going down here. The question is asking us to find the ratio of the speed of the alpha particle to the oxygen nucleus. In this question, we can consider the vertical components. If we consider that the alpha particle was initially traveling just in a horizontal direction, and we know that the momentum, because of conservation of momentum in these two directions, must be equal but opposite. So the momentum up here is given by P alpha sine 64, and here by P, the momentum of the oxygen atom, times sine 51. So we know that these two components must be equal in magnitude. So P alpha sine 64 is equal to P oxygen sine 51. Okay, so rearranging, we have P alpha over P oxygen is equal to sine 51 over sine 64. And we can rewrite this. The momentum is given by m alpha, v alpha, and the momentum for the oxygen nucleus is mass of oxygen, v of oxygen. And we're told in the question that the oxygen nucleus is 4 times the mass of the alpha nucleus. So we have m alpha v alpha over 4m alpha VO. Those will cancel. And so we end up with V alpha over V oxygen, this is for the oxygen nucleus, is equal to 4 times sine 51 over sine 64. So we just need to type this expression into the calculator. When we do that, we end up with 3.46. So these angles were two significant figures, so let's give that as 3.5 for our ratio. As it's a ratio, it doesn't have units. And that's the answer.